This is our third type of bond, which goes, you guessed it, for metals and metals, right? So what is it? These metals are arranged side by side in a regular repeating pattern. This pattern we call lattice, so that's how scientists call it, but it's really just a pattern of them being really pretty organized. And in here, all atoms give up their outer shell electrons, becoming cations. See how all of them became positive because they gave up electrons, so they can form this sea of electrons floating around all of them. They share them. See? So if you ask me exactly what is metallic bond, I would say that it is the electrostatic attraction that holds all of them together. There's an attraction from positive and negative, all the way around, right? That's what keeps them super together. Okay, why? Let's get back to the periodic table one last time. Okay, here we go. Now, exactly like covalent bonds, but the total opposite. We have metals, right? So neither of them has a very good electronegativity. Again, the ability to hold their electrons. So that's why they all straight up gave them up, because they just don't have this ability. And the ionization energy, how hard it is for them to give up their electrons? Absolutely nothing. It's super easy for them to give them up. So what do? They give them up. Then, electron affinity. How much do they want an electron? How much do they say this electron must be mine and only mine? Well, not much, right? Not really. It's literally opposite sides. So that's why they all share them. They're like, I really don't care. So they're just floating around in a sea of electrons. So that's why that happens between metals, and that's why it works. So let's start with our examples. We have iron, copper, aluminum. They are all metallics bonds because they're all metals in our lives. Here we have, for example, sodium, which is really weak because each atom gives up only one electron, right, to the C. So it's really not very attractive. It doesn't have a lot of attraction because there are not enough electrons there, so it could be considered as weak. Then we have potassium, which is even weaker than this one because they give up exactly the same amount, which is 1, but they have more volume to cover. So remember, just like in electronegativity, the more there are of electrons for the nucleus to pull in, is the less energy there are in their outer shells, right? So that's why there's more volume to cover. There are more electrons to be attracted, which means that they are less attracted because you have to give a little bit to everyone, so you have less for yourself, and that's why it's not as strong. Then we have magnesium, which is stronger because each of them gives 2 electrons to the C, so they can hold together much stronger. So now let's close up, okay? Let's finish.